Stanford University.
Today, my main purpose is to go through a very famous theorem, and it's the theorem which is the classical mechanical analog of the kind of reversibility that we talked about in, I think it was the very first lecture. Remember, arrows pointing in, arrows pointing out, and some rules about reversibility. And I said at some point we would get to the real thing as it stands in classical mechanics and how it is similar to what we talked about that first lecture. The theorem is called Liouville's theorem. And so today, at least for a good part of the lecture, I will talk about Liouville's theorem. But first, I want to remind you about Hamilton's equations, phase space, Hamilton's equations, and while I'm at it, to show you how Hamilton's equations lead to energy conservation. That, of course, is an important thing. We've seen how Lagrange's equations lead to energy conservation. And what was it? It was conservation of the Hamiltonian. So it will not be surprising in any way that Hamilton's equations, which are really just a repackaging of Lagrange equations, lead to energy conservation. Incidentally, even before I get started, everybody asks over and over again where these equations come from. Why, and I always tell you quantum mechanics is at the root of them, and of course that's true. But you might have asked a slightly different question. If quantum mechanics is at the root of them, what was Hamilton and Jacobi and Lagrange and Poisson, what were they all doing? They didn't know about quantum mechanics. They had no idea about quantum mechanics. What were they doing playing with this stuff and creating these houses of formal houses of cards and structures on top of structures on top of structures? Very, very beautiful, extremely beautiful. But where were they getting all of this from? And as near as I can make out, they were playing with the equations and finding structure there for its own sake. To what extent they realized how deep an aspect of nature these equations were, I don't really know. And I really don't know what drove them other than playing with the equations and finding formal structures there. So we're kind of working logically backward from quantum mechanics to classical mechanics, and starting with classical mechanics, whereas the logic goes the other way. But historically, we're doing it the way it really happened historically. And so it's very interesting what kind of weird minds these people had that were putting these things together in this way, and just creating formal structures. Formal meaning, mathematical structures with just for the love of the beauty of the equations, as far as I can tell. And Hamilton's equations was one of those structures that was discovered. Lagrangian equations were an earlier one. Newton's equations, of course, were even earlier. Newton knew why he was doing his equations. He was trying to explain the orbit of the moon, the orbit of the Earth, and all that stuff. What was Lagrange doing? I think he just noticed the similarity of the equations with the equations of optics, or the least action being similar to or the equations that come out of least action being not too different than the equations that would come out of least time. So I think he's just playing with it. And Hamilton, even more so, was just taking the structures, the mathematical structures that appeared, and reassembling them in all kinds of interesting ways.
A question?
Yeah.
You said that Newton didn't discuss kinetic energy.
No, I don't think Newton had a concept of energy. To my knowledge, Newton did not talk about energy.
What was the first?
I'm not sure. I'm not sure. I don't know. I'm not sure.
Okay.
Well, we could look it up. It's something we can look up on the internet. I'm not sure. Well, maybe somebody can look it up and tell us. I'm not even sure if it was a physicist. It might have been a chemist or...
Heat, from heat, maybe? Or no, that would be...
Yeah, yeah. Certainly by the time of Carnot, there was a very clear concept of energy. No, I must know. It was earlier than that. I mean, it was surely.
Leibniz, Leibniz had a concept of what he called Reversibility, which is twice the kinetic energy.
Leibniz.
Yeah, Leibniz.
Leibniz.
Yeah.
Might be. Yeah, he may have been the one. I don't know. However, we have it and we can use it.
Well, heat was thought to be a substance.
What's that?
Heat was thought to be a substance at that time.
Heat was thought to
So
be
you
a
have a
substance.
conservation of substance.
Right. But the idea of transmutability of heat into work into heat somehow was there.
Well, that's why physicists left.
Yeah.
Because of these concepts.
Okay, let's get started. Let me write down Hamilton's equations for you again, and then just show you in a couple of lines that they do imply the conservation of energy, which means the conservation of the Hamiltonian itself. All right, so we suppose that we have some system characterized by a bunch of Q's and a bunch of P's. We can put some little index under them to indicate which one we're talking about. For each Q, there's a P. For each P, there's a Q. And in Hamiltonian mechanics, the laws, or the law of nature, or the collection of equations of motion, are packaged in the form of a Hamiltonian function of the Q's and P's. H of Q and P. I won't bother writing little indices unless I need them. H of Q and P is the basic object of the theory. And how is it connected to the equations of motion? It's connected to the equations of motion through Hamilton's equations, namely, I always have to remember where the sign is, P dot is equal to minus dH by dQ. We'll put an index here. The 15th P, its time derivative, is equal to the derivative of the Hamiltonian with respect to the 15th Q. All right, so they come in pairs, and there's a Hamiltonian equation like this one for each I, and the other one is Q dot I is equal to plus dH by dP sub I. Now, H can be a complicated function of all the Q's and P's, so each right-hand side here does not just depend on one label here. All the i's appear in H, and so this equation can say that P1 dot is some function of P1, P2, P3, all of them, and likewise here. Okay, but the equations come in pairs. All right, let's write down now the time derivative of the energy, which means the time derivative of the Hamiltonian, and see if we can calculate it. That's just dH by dt. This is the total derivative, the complete explicit derivative, not the explicit, the complete derivative of h with respect to t. And h can vary because either p varies with time, or q varies with time, or both vary with time. And so that's equal to the derivative of h with respect to p times the time derivative of p. Let's put an I in here, plus the derivative of h with respect to qi dot. H changes with time because h changes with p, and p changes with time, and at the same time, h changes with respect to q, and q changes with time. That's what this means. All right, now let's just plug in Hamilton's equations for the p dot and the q dot here. All right, so let's put in here p dot. This is equal. There's a minus sign. dH by dPi, dH by dQi. Oh, sorry. There is, of course, a summation here. This means sum over all I. So let's put the sum in. I don't have room for the sum. Put it this way. Okay. Good. I won't bother writing it again. I intend there to be summations over I in these equations. the h by dp sub I, the h times p sub I dot, but p sub I dot is minus the h by dq sub I. So there's a minus sign, dq sub I, then plus the h by dq sub I, and now q sub I dot. Q sub I dot is the h by dp sub I. Nope, no dot. I. Dot my i's, not my q's.
Would the H have a dependence on time also?
That's a good question. If it does, then there would be another. Okay, so let's not include it in the same color, but let's just include it as an additional possibility that H might depend explicitly on time. Because some parameters of the problem are changing with time, then there would be another term here, the H by dt. And this means the change in the Hamiltonian, keeping P and Q fixed, but the change with respect to time because some parameters in the problem might change with time. Okay, so that's a good point. But of course, the essential point is that if the system is translationally invariant with respect to time, which is another way of saying that the parameters of the problem don't change with time, for a closed system where everything has been taken into account, we expect that the parameters don't change with time, then in that case, this would be 0, this red piece here. And the black piece, you'll just notice, is just written the same thing twice, once with a minus sign. So it's just plain 0. That was easy. So in Hamiltonian form, the conservation of energy is just that this is equal to minus this. You add them together, it's all equal to 0. 0. And if there is an explicit time dependence in the Hamiltonian, then, of course, the energy of the system would not be conserved. As I've emphasized over and over, the meaning of that is usually that there's some other second system that is moving in such a way as to share and exchange energy back and forth with the system you're talking about. But let's not take that case now. Let's just take the simple case where the Hamiltonian does not depend explicitly on time. Time translation invariant. Then it's a one-step, one-line thing to see that the energy is conserved. And another way to say that is to say, take the surfaces. This is a space here of some number of dimensions. If the number of q's is n, then the total number of dimensions in the space is 2n, nq's and np's. And write down the equation that h is equal to E, where E now is just a number. It happens to be the energy of the system, but let's just think of it as a number. Then the solutions of this equations are just some contours, some surfaces in the phase space. The phase space is the PQ space, and surfaces of constant energy. One equation in an n-dimensional space. Here's an n-dimensional space. It's got to be even, strictly speaking, but I can't draw an even. All right. One equation among a collection of unknowns or a collection of variables gives you a surface of one less dimension. If we have 2n dimensions for the q's and the p's, and I write down an equation like that, it defines some surface in the space. How many dimensions does the surface have? One less than the total number of dimensions. That's what writing one equation does. Okay? So what this says is that the way the system moves through the phase space, the motion through the phase space, stays on surfaces of constant h. The trajectories through phase space stick, so to speak, to surfaces of constant h. There are many surfaces of constant h. As I vary the value of h, I make different surfaces through here. I'm not going to try to draw another surface on top of that. But the point is, once the energy is fixed, the system will continue to travel on that surface. It doesn't have to go in a closed surface like this, a closed loop. It just will stick to that surface. An example that we talked about was the harmonic oscillator. For the harmonic oscillator, the Hamiltonian was omega, just a number, times p squared plus q squared. P squared plus q squared is or omega times p squared plus q squared is a constant. That's a circle. All right, we start with a two-dimensional space, p and q. We write one equation, p squared plus q squared is a constant. That defines a circle, which is one less dimension. We have different circles corresponding to different total energy. And the way the system moves or behaves with time is wherever you start the system, it will stay on the same circle, just orbit around that, around the origin. So that's another idea that the surface, yes?
Okay, you've got four equations there, p squared plus q.
Four equations.
No, I'm saying is, I'm trying to see, so for p and for q, you've got one equation each, is that what you're saying, or two equations each?
The equations of motion are these. There are two equations of motion. It follows from these two equations of motion that the time derivative of the energy is zero. That says that or the time derivative of the Hamiltonian. That says that the Hamiltonian is a constant in time. So let's call that constant E. Okay? The constant, of course, is determined by the initial conditions. Whatever the initial energy is, that's what E is. And each value of E corresponds to a surface in the phase space of one lower dimension. And the rule is the motion of the phase point, let's call this the phase point, through phase space, stays on the same surface of constant energy. That's one of the many consequences of these equations here, that the motion is on a surface like that. Okay?
Excuse me. The way you present this, there's really no relationship between the P's and Q's. This is just all very axiomatic.
Yeah. Well, it's not that there are no relations. The relations between them are given by these equations.
That's right.
Right.
But,
Yeah.
okay.
Yeah. No, that's right. For example, there's no automatic assumption that P is equal to the mass times Q dot. Right. You take whatever the Hamiltonian is, and we'll work out some examples which are non-standard. But basically, the Hamiltonian can be any function of Q and P. In many cases, you can write it as a kinetic term, that's what P squared is, plus a potential term. But by the time we've gone this far, we can write many, many other kinds of Hamiltonians. The only question is, do they correspond to anything in nature? The answer is often yes. But now, as you say, I think you put the right word on it. The axiomatic, this is an axiomatic theory now of mechanics, or a formal structure, or whatever you want to call it, and that defines it. Okay, so now let's move on to the idea of a flow in phase space. Let's go back to the harmonic oscillator for a minute. And instead of taking a given initial condition and a given starting point, a particular starting point, for example, this point, and then watching the phase point move around in a circle, let's imagine all possible starting points and indicate them by points on this plane, and in fact, think of a sprinkling of them. So uniformly distributed through here. Every one of them moves. And in the back of my mind, I'm thinking that the sprinkling of points can be thought of as a fluid. Not a real fluid, but an imaginary fluid composed of a huge dust. Think of it as a dust, but a fluid dust, where all the particles of the dust move in a way which is dictated by these equations. So wherever you happen to be, you'll be at the next point a little bit later. You'll move in some way, and some way is dictated by what the Hamiltonian is. And so you get a pattern, a picture of a flow. In this case, for the harmonic oscillator, the flow is very simple. Just everything sort of rigidly moves around on a carousel, so to speak. everything just rigidly moving around. And so the fluid has an extremely simple kind of motion. And it's not important whether this is a fluid, whether any real fluid could move like this. This is a secondary question. Just picture it as a fluid or a collection of a dust moving around like that. More generally, for an arbitrary phase space, always even dimensional, but I can't draw it even dimensional, you can play exactly the same idea, that the phase space is filled up with a dust. The dust corresponds to every possible starting point, and then just start the clock and let it go, and the dust moves through the phase space and defines a flow of a fluid, a flow of an imaginary fluid. We're interested in the fluid, and we're interested in the properties of it, but we're interested in one very specific property, the property called having a divergence or a convergence of the flow, a divergence of the flow.
You said it's a rigid thing, so you're implying that they all have the same period.
In this case, they all have the same
Period.
area?
Period.
Period, yes, that's exactly right. And what is the period? It's determined by this frequency. Well, this is a harmonic oscillator. Harmonic oscillator, no matter how far you displace the coordinate, it oscillates back and forth with exactly the same frequency. So right, so that translates into the statement that everything moves around rigidly. Right, exactly so. All right, so now we come to just a little bit about fluid, about flow vectors. Flow vectors and how they're connected to this and the properties of those flow vectors. A flow vector is a very, very simple idea. Incidentally, we're imagining a flow which is a kind of stationary flow, points move, Their motion, what they're doing next, only depends on where they are on the phase space. Where this particle moves next, in other words, what its velocity is. Not the velocity q dot, but the velocity in the pq space. What are the components of the velocity? What are the components, first of all, of position in the qp space? Q and p, okay? What are the components of the velocity in that space? Not the honest velocity of mechanics, but the velocity in phase space. Q dot and p dot. So we make a little vector out of them. All the q dots and all the p dots. Q dots and line them up. Q1 dot, Q2 dot, blah, blah, P1 dot, blah, blah, blah. Line them up and make a vector. Make a thing whose components are the vector. And then that velocity vector can be thought of as a vector in the phase space. A vector in the phase space showing the direction of flow. What is the flow? It's just these p dots and q dots. This is the velocity vector, and they're given entirely by known functions, if we know the Hamiltonian, known functions of position in that space. The right-hand side are known functions of the position, which are determined by the Hamiltonian. And so it means whenever a point in the flow gets to this point, it always has the same velocity. The velocity being determined by the value of h and its derivatives at that point. All right, so that means that we can take this space and fill it up with a vector field. A vector field just means a vector at every position. At every position in Q and P space, in phase space, we draw a vector which is just the velocity of the phase point if it's at that point. Kind of an ugly drawing I made, isn't it? Well, okay. Let's draw it for this guy over here, for this system. Is the velocity the same at every point? The velocity is not the same at every point. Even at a fixed radius, the velocity is over here in this direction. Do I have it right, or is it clockwise or counterclockwise? I told clockwise, isn't it? The velocity is this way here, this way here, this way here, and this way here. But suppose you're moving closer. Then the velocity is smaller. The magnitude of the velocity is smaller. It goes around in the same amount of time, but it has a smaller distance to go around. So the velocity, but this is not a very good circle around the origin. Here's a circle around the origin. The velocity is smaller here. And if you go in even closer, the velocity is even smaller. And so we fill the space up with a velocity field. Of course, over here it's this way, over here it's this way, here it's this way, and so forth. And that's called the velocity field of a fluid. Okay? It's called the velocity field of a fluid. And it's just a collection. It's nothing but these guys over here, P dot and Q dot. Okay. Now, the question I want to ask about this fluid is whether it's compressible or not. Whether it's compressible or not. Now, what does compressible mean? I'll tell you what compressible means by starting with an example of a one-dimensional example. Supposing I have a fluid which is a one-dimensional fluid. In other words, it's just a collection of points moving along one-dimensional axis. The fluid moves, and what I want to know is whether the points of the fluid get squeezed together and spread apart. In other words, whether the fluid is compressible. If the fluid is strictly incompressible, that means it has a constant density. You cannot change the distance between neighboring particles. For example, if the particles were little billiard balls, well, a one-dimensional billiard ball is a little weird, but one-dimensional little billiard balls, and they were up against each other, and there was no room between them, then you couldn't compress the fluid, and let's assume you also can't stretch the distance between them. Then we would call that an incompressible fluid. Now, an incompressible fluid, if we take the velocity field, at every point there's a velocity, and the velocity depends only on where you are. Is it possible that the velocity could vary along this axis? Well, if the velocity varied along this axis, I think it's pretty apparent. For example, supposing the velocity was relatively small over here and then jumped to something big out here. It's pretty clear that in the region where the jump took place, the points would have to be spreading apart. Okay? The points would have to be spreading apart. So the only way to have an incompressible fluid in one dimension is for the velocity to be absolutely constant and independent of where you are. It could depend on time, but we're assuming explicitly that the Hamiltonian doesn't depend on time. And so an incompressible fluid would be one for which the velocity vector had to be absolutely constant. So one aspect of the incompressibility is that if we look at a little segment of the fluid here, as much stuff comes in here as goes out here. The number of molecules that come in from here has to be the same as the number of molecules that go out here. Or better yet, the volume of a fluid in a small amount of time that passes into this little region here had better be the same volume of fluid that passes out of it. Otherwise, something has to get squished. Otherwise, something has to get compressed, or what's the opposite of compressed? Decompressed. Right. So I can immediately write down the condition for an incompressible fluid. We can think of it in two ways. One is to stay in the fluid at some fixed little element there and require that the same amount comes in from the left as goes out from the right. That's one statement of it. Or we can stick with a piece of the fluid and follow the piece of the fluid. And then to say it's incompressible is to say that the volume of that little piece doesn't change. Okay? To say it's incompressible if we follow the fluid, two ways to think. Follow the fluid, the volume of that piece doesn't change. If the volume changed, then it would be either expanding or contracting or compressing. And the other way to think about it is to stay fixed in the space, not move with the fluid, watch the fluid move past you, and say as much must come in here as goes out here. Both of those, they're equivalent statements, and to summarize them, the fluid is incompressible. But what is the condition for incompressibility? It's that the velocity has to be uniform right across this line. Or another way to write it is that the derivative of the velocity vector, let's call it the velocity vector, with respect to x, this is x, must be 0. What happens if dv dx, the velocity vector, if dv dx is positive? Let's just think about that for a moment. If dv dx is positive, that will mean that as you go to the right, the velocities are getting bigger and bigger. I would say that's decompressing. The fluid is stretching out. So if dv dx is positive, it sounds like it's the opposite of compression. And if dv dx is negative, that means that the velocity over here is large, smaller, 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 and maybe even turning negative and going the other way if dv dx is negative. It's clear that that's a compressional kind of situation. dv dx being 0 is the incompressible fluid. All right, now we're going to need the concept of an incompressible fluid for higher dimensions. One dimension will not be enough for us. So supposing we have a fluid in, well, let's begin with let's begin with 2 dimensions. We have a fluid in 2 dimensions, and either we can follow the fluid, take a little box in the fluid, follow it for a period of time. Its shape might change, I don't know what it does, but if it's incompressible, the volume, or in this case the area of that piece of fluid will stay the same. Or we can stand still and focus on a box here, and the condition of incompressibility is that as much fluid, volume of fluid, flows into this region in a small interval of time as flows out. For example, it might be flowing in over here and flowing out over here. Might even be flowing in over here, but then it better flow out over here, and so forth. That as much flows in as flows out. Now, I'm not going to work out the mathematics of this. Probably many of you know it, but I'll just tell you what the answer is. Supposing we have, in 2 dimensions here, a flow vector which is Vx and Vy. These are the components of the flow vector. They depend on where you are, x and y. What is the condition that fluid does not build up in this region? So first of all, let's go back to what we said before for the 1-dimensional case. If the fluid velocity is varying across the x-axis here, that's bad. It means it's either compressing, more fluid is coming in one side than going out the other. So we said that dv by dx better be 0. But it's pretty clear that dv by dx, let's write the partial derivative since we're now in multiple dimensions. The partial derivative of the velocity, and in particular the x component of the velocity, this is how the x component of velocity is varying as you change x. So if the x component of velocity is small here and big here, then the fluid is stretching. That's some measure of how much the fluid is stretching in this direction. But all we're interested in is following the volume. If the fluid is stretching in that direction, that's okay, as long as it's compressing in the other direction. If it's stretching itself out in this direction, it can still maintain its volume and still not be compressed if it's being compressed in the other direction.
Are you talking phase space or free
Phase space, phase space, phase space.
Isn't it also true for free space?
Yes, absolutely. Absolutely. This is a general statement about a fluid in any number of dimensions, that the condition that it's incompressible is not that the derivative of Vx with respect to x is equal to 0, but that the sum of them, derivative of Vy with respect to y, plus the derivative of Vz with respect to z is equal to 0. The first term measures how much compression there is along the x-axis. If the x component of, incidentally, as far as the x squeezing goes, the y component of velocity doesn't matter. What's important is how much the x component of velocity is changing as you vary x. And what these stand for is the combined sum of the compression along the x-axis, the y-axis, and the z-axis. Let's get these 3 coordinates now. Vz. And that's the condition that the flow of the fluid is incompressible. Now, this symbol, or this quantity, the derivative of the component of a vector field, the x component of a field with respect to x, plus the derivative of the y component of a field with respect to y, plus and so forth, has a name. Everybody know what the name of it is? The divergence of the vector field. The divergence, and it's a sort of measure of how the vector field is spreading out at any point. This is the divergence, and the symbol for it, there's a symbol for it which is del dot v. The del stands for the derivatives, the v stands for the vector field, and the dot product, it looks like it's a dot product between a del symbol and the v symbol, but it doesn't matter. This is what it is. This is what it is. The sum of the various components of the velocity field with respect to the same coordinate. It's called the divergence of the flow. It's the spreading out, or the compression. Now, having talked about this flow, and as I said, it's an equivalent question to ask if you stand at a point and require that the total volume of fluid that flows into that region is the same as the amount that flows out. That's equivalent to following the fluid and saying that in a chunk of fluid, the volume doesn't change. They're equivalent statements. Okay, let's abandon this whole line of thought for a moment and return to the very first lecture. And remember what we said. We had some kind of system which was characterized by some sort of space of configurations. Let's put another one over here. That's the that's a die with 7 faces. 1, 2, 3, 4, 5, 6, 7. Yeah. And we drew some arrows to indicate how the system moved. The arrows are in some sense very, very similar to this idea of a flow in phase space. They're telling you where to go next, is what they're doing. We gave some examples of good laws of physics. I'm not going to draw a good law of physics, but what is true of a good law of physics is that at every point, what flows in must flow out. That every point has an arrow coming in and an arrow going out. That if you're at this point, you know where you'll be next, and you also know where you were just before, unambiguously. Well, that's somehow saying something sounds a little bit related. If I take a little box around here, as much flows in as flows out. Right? One arrow in, one arrow out. We could even do something more. Let's go to the 6-sided case for a moment. We had laws of physics, for example, which looked like this. That was a particularly simple one. We could take a couple of points and we could follow them. 2 points to 2 points. They move around on this cycle here. 2 points to 2 points to 2 points. The number of points, if I start with 2 points and follow them, they stay 2 points. They stay 2 points. So in some sense, if we thought of the number of points as a kind of volume, the volume is conserved if we follow the system around here. Or we could say it the other way. If we focus on a particular node here, the number of arrows in is the same as the number of arrows out. by contrast with some bad laws. Here's a bad law. No matter where you start, you go to the central point. No matter where you start, you go to the central point. That's an irreversible law. You may know where to go next, wherever you start, but if you find yourself over here, you don't know where you came from. Okay? Well, if I draw a box around here, I notice that it's not true that as many arrows come in as go out. More arrows come in than go out. Okay? That's the nature of an irreversible law. So it almost sounds like in this discrete, simple-minded 6-state system or 10-state system, this one has 7, whatever it happens to be, that the law of reversibility sounds almost like saying that the fluid is incompressible. And in fact, if the fluid is incompressible, that sort of means that, well, it means something like this. It means a continuous version of the same idea, as much in as out. Okay? So the question then is the flow of the fluid in phase space dictated by Hamilton's equations, is it such that it's incompressible? Or another way of saying it is if you start with a volume in phase space, a little volume of phase space, and follow it in time, does it occupy the same volume afterwards? Or does it have an effect of getting squinched up so that things which were clearly distinguishable and different from each other get squished into a smaller region where they can be less distinguished? That's the question. So what I'm going to show you now is Liouville's theorem. Liouville's theorem is the theorem that says that the flow in phase space is incompressible. And it's the closest thing that we have, closest analog that we have to this idea that, well, this idea that as many points come in as go out at every point here.
Just to clarify, are the V's are P dot and Q dot?
Yes, the V's are P dots and Q dots. Right. So we line up all the P dots and Q dots. Let's think of our velocity vector. Well, I'll tell you what, let's start with just the case with one P and one Q, and then generalize it to any number of P's and Q's. So we have one P and one Q, Q and P. And what is the velocity vector at every point? The velocity vector, let's call it V sub P and V sub Q. These are the components of the velocity vector. And by definition, Vp is P dot and Vq is Q dot. Okay? So this phase space here is filled up with a velocity flow where the components are P dot and Q dot. Now let's calculate the divergence of the flow. The divergence of the flow is the derivative of Vp with respect to P plus the derivative of Vq with respect to Q. If you like, this one is telling us how much the fluid is bunching up along the p-axis in the p direction, and the other one is telling us how much the fluid is bunching up in the other direction. If it's incompressible, the sum of these should be 0. Okay, now we can work it out. What is Vp? Vp is P dot, but that's minus the derivative of h with respect to q, right? Hamilton's first equation. And q dot is equal to plus dh by dp. So you just calculate them, whatever they happen to be. You calculate them, they're functions of p and q, and they give you the components of the velocity vector in the phase space. Okay? Any questions? Good. Now all we have to do is calculate. The derivative of Vp with respect to p, here's Vp right over here. This is minus d by dp of dh by dq. And what's this one over here? This is plus d by dq of dH by dP. I think we must have mentioned at some point about partial derivatives that the process of partial derivatives is independent of the order of the differentiation. I think I hope we mentioned that, because if we didn't, we'll mention it now. If you have the second derivative of a function with respect to two independent variables, it doesn't matter which order you differentiate. That's a little theorem. It's a very simple theorem. I can show you on the blackboard why it's true. But I think did we do this in class? Never? Oh, we didn't. It's clear? All right, get up and prove it. Let's prove it. Let's prove it. Let's label 4 points here, A, B, C, D. And we have a function of the 4 points. All right. This direction is P, and this direction is Q. All right. What's the derivative of the function with respect to Q down here? Well, let's call it VC minus VD, right? We should put a little epsilon in the denominator, but basically the derivative of some function, and whatever function it happens to be, function. The derivative of a function with respect to Q is just the derivative as you move along the Q axis. Okay? Now, what's the derivative with respect to Q up here? That's f of B minus f of A. So now, let's consider the derivative with respect to P. That's differences going vertically of the derivative of f with respect to Q, d by dP. That's just the difference of this and this, right? It's a difference of differences, but the difference, this one tells you to move vertically, this one tells you to move horizontally. So the difference between this expression and that expression is just this mixed derivative here. Let's write it down. F of B minus f of A minus f of C plus f of D. F sub C, f of D. So this minus this. Okay. Here's another way to write it. It's f of B plus f of D minus f of A minus f of C. But that's neat. Look what it says. It's f of B plus f of D minus f of A minus f of C. So it's this one plus this one minus this one minus this one. That's what the second derivative is. This one plus this one minus that one plus that one. But now think about the other order of differentiation, d by dq of df by dp. If you just spend 1 second doing it, doing the same thing, you'll find out it's exactly the same thing. I'm not going to work it out. It's the difference, it's the horizontal difference of the vertical differences. You know what I mean? It's exactly the same expression. So it doesn't matter when evaluating this combination here, it doesn't matter whether you think of it as differences going this way or differences going this way. You know what I mean? It takes too many words to express it. This is an example here. The second derivative with respect to P and Q of H is the same as the second derivative with respect to Q and P of H. So what's the net upshot? This is 0. This is Liouville's theorem, that the flow is without any compression or decompression, that the divergence of the flow vector is 0. And it's a consequence of Hamilton's equations. What it says is in this phase space, this two-dimensional phase space, as you watch the fluid flow, there's no buildup anywhere, and there's no tendency for the fluid to compress, to rarefy, or to get more dense. Now, what about any number of Q's and P's? No difference. You just put an I in here. I. Same deal. It's just a multiple version of exactly the same thing with any number of dimensions. In each pair of directions, each Q and P, the flow along one axis is compensated by the flow along the other axis. The way to say it then is that if you take a piece of this fluid in phase space, a collection of points, and you either two ways to say it, as I said, follow it, the volume of it in the phase space doesn't change, or stay at one point, as much comes in as goes out. That ensures, incidentally, that points in the phase space cannot come together and coalesce and lose memory of which point was which. They maintain their integrity. They don't stay the same distance apart, but each one occupies a little volume which is sort of sacred, and the other ones can't penetrate it and lose their individuality, so to speak.
Are you assuming a summation in that?
Yeah, absolutely. They cancel in pairs, which is a special version of incompressibility. It means in pairs of directions, the compression in one direction and the decompression in the other have to cancel. So it's a special kind of incompressibility, but it is incompressibility. It's a stronger kind of incompressibility. It's stronger than incompressibility, but it's not weaker than incompressibility. And so and as I said, it is the closest thing that we have for the continuous world to this idea that there's no convergence of the trajectories in the discrete world, no loss of information.
A question. So
Yeah.
the expression that you've written for divergence, that's the way divergence looks in Cartesian coordinates.
It is.
And I assume this result is going to carry over to other kinds of coordinates?
No, phase space is always thought of as Cartesian. Phase space is thought of as Cartesian. In this sense, well, it's called symplectic. It's not really Cartesian, but it's Cartesian is close enough to us. Yeah.
With this, I'm not trying to confuse things, but would this hold for like the notion of an expanding universe with a coordinate system?
Yes, that's a good question, and the answer is yes. But even more simple, let's talk about taking a box of gas and expand. Oh, incidentally, this theorem does not really depend on the Hamiltonian not having any time dependence. Time dependence, it wouldn't matter. It's still true, the Liouville's theorem. But okay, so we take a box of gas and we expand the box of gas. It's almost like the universe expanding. What happens? Well, the real fluid, the ordinary sense of fluid, the positions of the molecules in real space, they're obviously spreading out from each other, right? So the fluid in ordinary space is not incompressible. It's being rarefied in this case. What that means is that in the p space, the momentum space, the points must be getting closer together. The points must be getting closer together in momentum space, and that's true. That's a correct statement. That if the fluid is expanding in ordinary Q space, it means it's contracting in the p space. The momenta are getting closer to each other. Now, let's think about that for a moment. What does happen to the momentum of particles in a gas if you expand the gas? It goes down, right? They get closer to zero. And they all get closer to zero, so the gas is getting compressed in the p direction while it's getting expanded in the x direction. If you squeeze the gas, exactly the opposite happens. So yes, it does. It is an important aspect of an expanding universe that the same thing happens.
So what if it's a sudden expansion, so the particles...
Still, doesn't matter how fast the expansion is. This theorem has no assumption in it that the parameters are not changing suddenly with time. I know what you're thinking. You're thinking about entropy, but phase space volume is conserved. Look.
I missed, so is a 5-particle system 5 points in 2-dimensional phase space or 10-dimensional phase space?
Say it again.
If you have 5 particles.
10-dimensional phase space.
So those points there wouldn't represent individual particles, they represent individual states.
Yes, they represent individual states. That's right. They could, of course, they don't represent individual particles. They represent states. That's correct. Well, right. The points represent states, and then we imagine fictitious particles. Fictitious particles are in this higher dimensional space. That's right.
So I have a question I think is related to what you're talking about. It seems pretty easy to see how Leuville's theorem follows from Hamilton's equations for the phase space velocity field.
Mm-hmm.
But I'm kind of fuzzy on what this fluid is. You know, what are all these, like, what's the initial density? Well, all these points are different states of the system.
Yeah.
If I don't think about the fluid, it all seems straightforward.
Yeah. You don't have to think about the fluid. You don't have to think about the fluid. Forget the fluid if you like. The fluid is just to visualize. And physicists always draw the fluid because it's a useful trick to visualize. But here's the statement. Take a patch, a region of the phase space. Every point in this phase space goes somewheres after a certain period of time. Are you with that?
Yes.
Okay. That means this patch will move. Okay? The moves in a way which preserves the volume in phase space. The volume in phase space means the product of P and Q, the integral over P and Q of, or just the ordinary volume in the PQ space. Just normal concept of volume. Normal concept of volume, but not spatial volume, but volume in QP space. Now, it's an interesting question. Supposing you change coordinates in some very complicated way, that will also entail a change of the definition of the momenta. Will, if you reparameterize everything by some totally different coordinates, will the theorem still be true? The answer is yes. So,
The way you've drawn it also implies a relationship of the movement, that you don't have some going up and some going down.
you might have some going up and some going down, but then you also be likely to have some coming in and some going out to compensate.
Well, I was thinking about the way you get a very complicated drawing if you have some of those arrows going one way and some going the other.
Good, so let's take an example. Let's take an example. I think what you're saying is that the shape of a region of phase space could change. And it could change in radically complicated
Yeah,
ways.
well, this is a simple change, but if you had some of those arrows going this way and some going others, then it's a very complicated.
It could be. Let me get, let's construct an example. I'll come back in a moment for a question. Here's a Hamiltonian. It may be a little bit unusual, but it's a perfectly good Hamiltonian. And so we can write it down and we can study it. Not p squared plus q squared, but just p times q. Let's see what that one does. Hamiltonian is p times q. What is Vp? Vp is the same as p dot, and that is equal to partial, or that's equal to the partial derivative. I'm going to get rid of some of the equations in a moment. That's minus the partial derivative of h with respect to q. And what is that? Minus p, right? Okay. So the first equation is Vp equals, or let's write it as P dot. I'm not going to call it Vp. Let's just call it P dot. P dot equals minus P. Supposing P is positive for a moment, what happens to P as time goes on? You get bigger or smaller? Right. What happens if P is negative? What happens to it in time? It gets bigger, but in magnitude, it also gets smaller. In fact, what's the solution of this equation? P dot is equal to minus P. It's an exponential, but a negative, a shrinking exponential. So P shrinks. Whatever P is, it gets smaller with time. In fact, it exponentially gets smaller with time. That sure sounds like the fluid is compressing along the p-axis, and it is. And it's compressing violently as time goes on, since it's being exponentially shrunk. What about q dot? Q dot is equal to plus dh by dp. And what's that equal to? That's equal to q. So what happens to the q motion of the fluid? It exponentially expands. So it's contracting in one direction and expanding in the other direction. That means if I were to take a little square patch, it would spread in the q direction and shrink in the p direction. It spreads in one direction by the same factor that it shrinks in the other direction, and the result is the area stays the same. But the shape can change a lot. So this was just a simple example of a case where you can, we can violently make the shape of, but the volume stays the same. Well, just a second. Oh, there's a question over here. Before we do anything else, let's just check that the divergence of the velocity is 0. Here's the velocity. That's Vp is minus p. Vq is q. What's the divergence? It's the derivative of Vp with respect to p. That's minus 1. Plus the derivative of Vq with respect to q. That's plus 1. If I add them, I get 0. So the divergence of the fluid is 0. The two kinds of motion canceling each other. Okay, now question.
So since PQ is action, is Liouville's theorem equivalent to the conservation of action?
No, it's not the conservation of action. It's the conservation of volume in phase space. It's the conservation of volume in phase space. Why do you identify it with action?
PQ has units of action.
Oh, it does have. Indeed, it does have units of action. It's more closely related to entropy than it is to action, but there are circumstances in which entropy and action are simply related. PQ is not the action, but it does have units of the action. It also has units of angular momentum, but it's not the angular momentum either. And you might begin to guess that it has a lot to do with quantum mechanics, because in quantum mechanics, the basic rule of quantum mechanics is that action is quantized, and so these little areas in phase space, well, we'll get to it. Let's not jump ahead. You're touching on something important, though, when you point out that this has units of action. But it is not, strictly speaking, the action. Yeah?
Do the rules allow you to break it up, or is it?
Break what up? Oh, that's a wonderful point. In other words, the question is, the answer is definitely not. But the question is a good one. The question is, supposing you start with a volume of phase space like this, could that volume go to this and then pinch off and break up into two separate volumes? The answer is no. I'd have to think about proving it. It's not too hard to prove. I think that was a question, was it? Yeah. No, the other part of the theorem, a little more complicated to prove, I have to think about it, is that the topology of a region of phase space doesn't change. And as I said, that can be proved. The way you prove it is by going to the point where it's just barely touching. And then you go to that point right over there, and you say, which way does that point go? Does it go this way, or does it go that way? It's the same point in phase space, and the direction that it goes in is not ambiguous. It is determined by the Hamiltonian, and it only gets to go in one direction. So because this point among all other, and all other points are completely deterministic where they go, it can't split.
Politics, they call it gerrymandering.
What's that?
Politics, they call it gerrymandering.
Politics call it gerrymandering, right. Right. But it can, but what it can do, there's absolutely nothing that says that it can't generate a very long, thin string like that.
So is that related to your statement before that points can't coalesce?
Yeah. 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 But the important thing is that you can think of each point as having a little volume that, an integrity that doesn't allow other ones to jam into it, so to speak. Like little incompressible particles or billiard balls at the...
Question. Is there an application for Liouville's theorem in terms of solving something? Sure.
Oh, yeah. Yeah. Take a gas and put it in a box and expand it. What happens to the velocities? Well, basically the answer is if the expansion increases the volume of ordinary space by a factor of 2, it will decrease the momenta by a factor of 2, and as a result, cool the gas a very, very definite way. Yeah. In thermodynamics, it is absolutely central to the conservation, well, to the concept of entropy, and it is the reason, from this point of view, why when you expand the gas, it cools.
Don't trajectories overlap for the solid pendulum, for example?
No. What's a solid pendulum?
A pendulum with a solid rod instead of a string when it's standing straight up. Clockwise versus counterclockwise.
Okay. Yeah, you're asking, that's a good question. Supposing you're at a point of unstable equilibrium, and you start right up here, then this point does indeed go in a different direction than this point, and that's exactly the situation where you get these very, very thin threads forming. Well, let me come back to it. What I wanted to talk about before doing that was to talk about the kinds of systems that don't have Liouville's. Yeah.
I'm just thinking that the thought thing is that it gives the illusion of two separate entities, but they're entangled.
Who?
When you take and do that, stretch it.
This?
No, the
this?
picture you drew there, but the two things separated by a great distance but still connected.
Mm-hmm.
That be considered like giving the illusion of two different things but entangled?
Not entangled.
Well, connected.
Well, they're not physically connected to each other. This doesn't mean that they're physically connected to each other and exerting forces on each other or anything. It just means that
I'm saying it's really one entity, but...
Well, it's one blob of phase space. It's not an entity. It's a blob. It's a blob of phase space that you first drew, and you followed it. You just followed it. Each point in here is a different initial condition. It's different. All it is. That's what it is. It's a different initial condition, and now you follow the initial conditions in phase space. And some of them separate, some of them grow together in some directions, but always in a way that conserves the volume. Let's take an example of a system that doesn't conserve the volume in phase space, just to see what the difference is. Now, I've already proved that the volume in phase space is conserved. So how can I take a system which doesn't conserve the volume in phase space? Well, I proved it by starting with Hamilton's equations of motion. So I will have to take a system which doesn't have a Hamiltonian, which doesn't have for that matter, a Lagrangian, and which therefore violates the rules. Very simple system. The damped harmonic oscillator. The damped harmonic oscillator is a harmonic oscillator where the bob of the oscillator, or whatever you call it, is moving through a viscous fluid. What happens, first of all, what happens to the damped harmonic oscillator with time? It just runs down, right? It starts to oscillate. What happens to the position x? It goes to 0 with time. What happens to the velocity v? It goes to 0 with time. After a long, long period of time, you can't tell where it came from. It doesn't seem to have this character of being, but let's see exactly what happens. Well, we could work out the equations. Let's work out the equations. The equations are mx double dot, that's acceleration, is equal to force minus kx. That's the harmonic oscillator, the restoring force. So far, no problem. And then I'm going to add something which is the viscous drag force minus a constant times x dot. That's a velocity-dependent viscosity term, and it's a force which depends on how fast you're moving through the fluid, and it's viscosity. Viscosity cannot be derived from a Hamiltonian. Where does it really come from? It comes from the enormous number of particles colliding, and it comes from the statistics of them, and it comes from places that we're not going to try to get into now. But this is the equation of motion for a damped, not damned, not D-A-M-N-E-D, but damped, D-A-M-P-E-D, damped harmonic oscillator. Okay, what does it do? Well, the ordinary harmonic oscillator, and let's incidentally, let's call mx dot, let's call that p. Even though there's no Lagrangian to derive it from, the real definition of momentum is the derivative of the Lagrangian with respect to velocity. In this case, this is not a legitimate system that comes from a Lagrangian. Nevertheless, since we're familiar with thinking of momentum as mass times velocity, let's call this the momentum. All right, then here's the phase space, p this way, x this way. And what does the system do now? If there wasn't for this damping term, it would move in circles. It would just move everlasting circles that would just went around and around and around. What really does happen is the viscous drag force sucks energy out of it. Remember that energy was just x squared plus p squared. If energy is being sucked out of it, it means the radius of the orbit is getting smaller with time. So if energy is being sucked out, let's say slowly, let's imagine this viscosity is small, then it just spirals in and gets closer and closer to the origin. You're right, it should be clockwise. Right. Okay. And in fact, it doesn't matter where you start. You spiral into the origin. After a long period of time, you could start with a patch of phase space that big, follow every point, and they all get shrunken down to a point, to a little volume very, very close to the center here. So evidently, this is a system that doesn't have a Liouville theorem, that the volume in phase space is not conserved. But let's check that by calculating the velocity field and calculate its divergence. Let's really do the calculation. Let's do it. All right. So first of all, you know what? I'm going to get rid of the mass and the spring constant and the constant here. And we're just going to simplify the equation to the bare bones. Bare bones, then x dot is just equal to p. Now what is p dot? I'm sorry I did that. X dot is p over m, or mx dot, yeah, p over m. All right? That's x dot. That's the x component of the flow, right? Vx. What about Vp? Vp is p dot. And what is p dot? Well, the left-hand side of the equation here is p dot, right? This is p dot, d by dt of mx dot. So here's p dot. It's equal to minus kx minus c times p over m. So this is Vp. Here's Vx, and here's Vp, and that's minus kx minus cp over m, right? This is just force is equal to restoring force plus viscous force. Viscous force is proportional to velocity, and velocity is proportional to momentum. Okay, now let's calculate the divergence of the fluid. The derivative of Vx with respect to x is what? 0. There's no x on the right-hand side. So the derivative of Vx with respect to x is 0. But what about the derivative of Vp with respect to p? Minus c over m. So the divergence is not 0. The divergence is not 0. In fact, the divergence is negative. That means the flow vectors are kind of pointing inward, not diverging, they're converging, and it's this over here, which is, so to speak, the velocity divergence, which is pushing everything into the origin. So we find consistency. The divergence of the fluid is not 0 if there's a viscous force. The viscous force cannot be derived from a Hamiltonian. And it violates Liouville's theorem. It doesn't violate the theorem, of course. It violates the statement, the conditions of the theorem. But it's a system where you really do lose information. You start it going, and after a while, the phase points lose their integrity, and they all get squished into the same small volume. So it gets harder and harder to distinguish the points of phase space. It's basically a sink. Yeah, it's a sink. There's a sink distributed throughout here. And it's playing the same role as this sink over here where all trajectories were leading into the same point. It's playing the same role. And it's the sort of system that cannot be a consequence of the fundamental laws of motion.
Is it possible to have a divergence of 0 for a system without a Hamiltonian?
Is it possible to have a... Oh! That's a good question. Yes. Yes, it certainly is. It certainly is. It certainly is. Yeah, the question, okay, so I think the question was, is it possible to have the divergence 0, but not have your equations come from a Hamiltonian? And the answer is yes. The answer is most certainly yes. So the Hamiltonian construction here is not necessary and sufficient for Liouville's condition, let's say. It's sufficient for it, not necessary. You can have system, you can have, not mechanical systems. I don't know of any mechanical system that works that way. But yes, a fluid. Let me give you a very simple example. A fluid in 3 dimensions. In other words, a real incompressible fluid, a genuine incompressible fluid moving in 3 dimensions. It can't come from a Hamiltonian because the phase space of a Hamiltonian system is always even dimensional. Right? So it just can't. But still, if the fluid was made out of a lot of billiard balls that were stuck together and incompressible, each billiard ball would have an integrity and could not get lost, and so it would have this character of being of not losing information, if you like.
Yeah. You said a number of times that the Hamiltonian development is sort of logically the same really as a Lagrangian, and that really is the same as Newton's equations. But doesn't the damped harmonic oscillator, isn't that described by Newton's equations?
Yes, it's described by Newton's equations, but it's not described by a force which is the derivative of a potential energy. No, it is not correct. Okay. It is not correct that, that the Lagrangian and Hamiltonian, okay, are equivalent to Newton's equations. That's incorrect. They're not the same as F equals ma. They're the same as F equals ma if the forces are derived from a potential. If the force is derived as the derivative of a potential, then they're the same. So, right, so Newton's equations are just F equals ma, and it doesn't tell you what the rules about the forces are. It tells you some rules, equal and opposite and so forth, but it doesn't tell you that they come from a potential. Yeah, Newton did not know about energy conservation.
No. What you just said about a three-dimensional fluid, okay, X, Y, Z, that's what you meant?
Yeah.
Okay, but that, in phase space, that's 6 dimensions.
No. Just take a system, a system of, I think the question was, supposing you have a fluid that's incompressible with a set of coordinates, does it follow that the equations of motion for that fluid, oh boy, that the velocity vectors derive from differentiating some kind of function of the P's and Q's? The answer is no. Example, a three-dimensional fluid with a velocity vector, forget whether it's a fluid, just a velocity vector in 3 dimensions, which corresponds to an incompressible fluid. Don't worry about it. The answer is that the incompressibility does not imply Hamilton's equations. Hamilton's equations imply the incompressibility of the fluid. It's a one-way thing.
Yeah, I want to go back to my last question. I'm going to pose a very simple system. You have 2 particles. They have 0 momentum. They're close together. Total energy would be 0. Now we take one particle and we move it out 13 billion light years. Then all of a sudden it has an enormous momentum because of the expansion of the universe. Is that, in other words, the momentum is a function of the distance, x. If you draw phase space, okay, do you see what I'm saying? I'm not sure if just the separation of the 2 particles implies some kind of energy because of the expansion. I'm not sure if I'm articulating this very well. But the coordinate system itself is expanding, where in normal space that doesn't happen. There's no expansion. Because you can, the Hubble constant, you can have things, separating faster than the speed of light, okay? Which has nothing to do with this, obviously, but
right.
But with a gas, the larger it gets, the smaller the momentum. But just looking at the expansion of the universe, the further the particles are separated, the larger the momentum.
You're talking about a different phenomenon, which I could describe in a different way. If you have an explosion, now this isn't expanding a gas by a controlled expansion. You just take a gas and you explode it. Particles don't even interact with each other, they just go flying out. It's not a surprise that the ones which are furthest away are the ones that are going fastest. Why are they further away? Because they were going faster. That's the expansion of the universe. Why are the distant galaxies moving faster? Why are they further away, you ask? Because they're moving away faster. That is the way Hubble's law works. That really is the way Hubble's law works, that the things which are maximally far are the ones which are moving away fastest. Why? Same reason. So it's a different question, yeah. The fastest horse wins the race, not surprising.
In this example with the damping where you have this spiraling in,
Yes.
aren't you really not losing information if you have infinite precision?
Okay, so, all right, so that's what I'm telling you is the closest thing that we have to the discrete losing of information or not losing information is whether or not the divergence of the velocity field is zero. I think what you can say in this case is that each little cell of phase space is not maintaining its integrity in the sense that it is not maintaining the same volume in phase space. That's about all you can say. You're right, if you had infinite precision and you knew exactly where that point was and exactly what velocity it had with infinite precision, you could reconstruct the past from the equations, yeah. But in practice, all of the phase points here are getting squished together and losing their individuality. You need a better and better microscope to disentangle what's happening here. There's a unit of size. Well, I don't want to get into quantum mechanics. No quantum mechanics tonight. So you're right. It is different than this very discrete situation where no microscopes are necessary and no enormous precision is necessary to identify a point among 6 points here. But it has a similarity. And the similarity is as many points flow into a point as flow out of a point. I think that's the bottom line. Yeah, that's as close as I can get to relating the two concepts of reversibility that we talked about. And of course, in quantum mechanics, where in a sense everything really is discrete, the Liouville theorem becomes much, much more similar to this situation here. The Liouville theorem is replaced by another theorem which is much, much more like this. The connection is that in quantum mechanics, there's a little unit of phase space, a smallest unit of phase space. The smallest area in phase space. That's what's quantized, the area unit in phase space. And what quantum mechanics tells you is that systems don't get bunched up into smaller and smaller volumes. But we'll have to come to that. That's a ways in the future. At the moment, the theorem is that volume in phase space is conserved. Shape is not. So think about it. Any other questions?
You started with a surface in phase space as what represents the conservation of energy or yeah.
Yes.
How does that relate to the flow?
Yeah, well, of course, among other things, the flow is along these surfaces, but that doesn't change the facts here. Right. That's. Let's go back to the harmonic oscillator. In the harmonic oscillator, the surfaces are these circles. So if you start on a circle, you stay on a circle. And that's a true statement. The other true statement is if we take a bunch of phase space here, little region of phase space here, and we follow it, it's not a definite energy. It's got just some little box with some volume. And follow it, it just moves around here rigidly, maintaining its volume. Two different statements. So they're not so much related. They're not so much related. Right. You can take a little volume of phase space, which includes several different energies, and follow it, and it will maintain its volume. Notice in this case, the shape of the region also is conserved, is maintained. So in the x squared plus the p squared plus q squared case, that's the harmonic oscillator, it's not just that the volume of a piece of phase space is conserved, the shape is conserved. In this other case over here, the volume is conserved, but things get stretched one way and compressed the other way. So this is, the harmonic oscillator is special this way. Yeah.
In Newton's world, you can change energy by doing work.
Yes.
Do we have the equivalent? How do we handle work?
Well, work is energy that's exchanged with a system that you're not accounting for. In other words, if I have a system, let's suppose it's this eraser here, and the eraser is satisfying some equation of motion, which has a gravitational force, a kinetic energy, and so forth, and I am an external system that's not being accounted for in the equations, exerting forces on this, then I can exchange energy with it, or I can change its energy by doing work on it, but the work, the energy that I give it, is taken from me. So work has to do with exchanging energy between systems that you're accounting for everything and other systems that are acting as external agents on the system. For example, well, yes, the concept of work is useful when you separate a system into the part that you're going to describe and the part you're simply describing by external forces. Where those external forces come from, you don't care. You don't care if they're described by a Lagrangian or Hamiltonian or anything else. You just say there's an external force on a system, and that external force on the system does work on it. It can just raise a weight. Of course, it changes the energy at the cost of having to provide the energy from the external system, which is doing the work. So, but the concept of work is not one which comes up very much in modern physics. So we don't really need to think about it. Energy conservation is the important idea. And the idea that two systems can give energy back and forth between them, and that we sometimes call that work, is so secondary. Yeah.
Just looking for connections, is there, Liouville's theorem says we preserve the topology of phase space. Does it do anything? Topology.
It does, yes.
It doesn't preserve angles, does it?
No, definitely not. For example, in this case, PQ here, if I took a cross like this and I evolved it, it would become a cross like that. No, it definitely does not say angles are conserved. Most definitely not. The harmonic oscillator is probably the only case where it's true. And that's an unusual case. Right. Yes?
Just to, I listened to your lectures on the tape from the previous series, and you, in the classical mechanics, you talked about Legendre's theorem. And
I decided to abandon, to not bother with it this time, but the Legendre transformation.
Right. Is it mostly mathematical, or is it physically significant?
It's a trick. It's a useful trick. It's a useful trick. It's especially, it's a useful trick. I decided it wasn't important enough to worry about this time around, and we didn't really need to think about it. If I ever need it, and we ever need it for anything, I'll do it. But it's right. We used it over and over, but I didn't call it that. Okay. I could go on for another few minutes, or we can just stop here. The next thing, as I said, a lot of this development of classical mechanics, which really did turn out to become absolutely central once quantum mechanics happened, was playing around with the equations and putting them in different forms and finding different elegant representations of the same set of equations. And we're going to do at least one more version of mechanics, or at least one other concept which is closely related to the Hamiltonian version, and it's called Poisson brackets. It's, again, one of these very elegant things when you look at it, you say, what the hell good is that other than for just writing neat equations? And the importance of it, again, quantum mechanics. Maybe I will start the subject of Poisson brackets right now.
At the beginning of the hour, because you just cycled back to what you were talking about at the beginning of the hour.
Beginning of the hour was energy conservation.
No, the very beginning, 7 o'clock, you were musing about the 19th century physicists, and you said that you were speculating that they had played with a lot of different equations and without realizing the physical significance of them.
Well, I don't know. They may have realized the physical significance within the context of classical mechanics. I mean, for example, Hamilton probably did realize that the Hamiltonian was energy. But what they were doing was just playing with the equations, I would say. I don't think they understood. They could not have understood how important it was going to be 100 years from then. There was no way that they could have. They were, among other things, they were finding analogies between different kinds of things. For example, the motion of light rays and mechanical systems. Well, once you know that the motion of light rays is like mechanical systems, you might begin to wonder, is there an analog in classical mechanics of wave motion and so forth? And the answer is yes, there is. But they were exploring all these analogies and mathematical similarities between other different things, trying to create structures where everything would fit into the same kind of structure, trying to make the equations as small as possible, meaning as few as possible, as elegant, as neat as possible. In my opinion, it was not so much motivated by individual phenomena as trying to unify everything and packaging it into the same kind of package. Formal structures, creating formal structures. But I wasn't there, I didn't do it, and I can only guess what was in their minds. They were largely, there was no difference in those days, or not much difference between a physicist and a mathematician. And, well, I first heard this remark from my friend Dick Feynman many years ago, that the difference between mathematicians and physicists is the difference between masturbation and sex. And, I think what he meant is that physicists are interacting with a partner, namely the physical world. Mathematicians are interacting. And I don't know what was on their mind. I wouldn't have done what they did, unfortunately. All right, let's talk a little bit about Poisson brackets, just to set us up for the next time. What is a Poisson bracket? Well, it starts out by saying, supposing I have a function of P and Q, the most general thing I could be interested in, thing having to do with the dynamics of a system, is to know how a function changes with time. Now, the function could just be Q, in which case figuring out how the function changes with time is just figuring out how Q changes with time, meaning how the position changes with time. It could be Q times P, And you ask, how does Q times P change with time? I don't know why you would want to do that. But, well, it could be the angular momentum, R times P, Q, which is a kind of Q times P. The angular momentum, if there's a torque on the system, then the angular momentum changes with time. You might ask, how does the angular momentum change with time? So how does the general function f of Q and P change as time goes on? Let's explore that question just as an abstract question. How does this change with time? And again, the number of tricks here is rather limited. I'm interested in how this quantity changes with time. Now, why does it change with time? It changes because Q changes and P changes. As you follow the trajectory through the phase space, f of Q and P changes just because Q and P change. All right? So how do you calculate this? Standard rule, you differentiate df by dq sub I, we're going to sum over I, times q sub I dot plus df by dp sub I, oops, p sub I dot. Same thing, we've done it before, we'll probably do it again. We differentiate something with respect to time by differentiating it with respect to the arguments, the thing that the function depends on, and then multiplying by how fast those things change. But now we have something, we have p dot and q dot. So I can substitute that in here. And this is equal to summation. Now somebody first did this calculation. I don't know who it was. Maybe it was Poisson. But let's write it out. df by dq sub I. Now what's q sub I dot? dh by dp sub I, right? Minus? Q? No, that's right. And then there's another term, which is df by dp sub I. And then p sub I dot that does have a negative, dh by dq sub I. Two functions. One of them is h, the Hamiltonian. The other is some general function. Poisson did this calculation, and he did it for the harmonic oscillator, and he did it for this system, and he did it for that system, and he got tired of writing this down. He wrote it down so many times for two different functions that he decided to give this operation a name, or to write a symbol for it. And so he said, given any two functions, whatever they happen to be, let's now take any two functions. They don't have to be, one of them does not now have to be the Hamiltonian. This is just a definition. Let's replace it by some general function, which we'll call g. May or may not be the Hamiltonian of the system. Just two functions of phase space. This quantity, the derivative of one with respect to q times the derivative of the other with respect to p, and then interchange and subtract and sum over I. That Poisson called the Poisson bracket. Poisson was not a modest man. It's called the Poisson bracket of f and g. And it's simply written f comma g. We're going to write this kind of thing down now and then, and we're not going to bother writing all of this mess here. We're going to write, it's the Poisson bracket of f and g. But now we have a new way of writing Hamilton's equations and everything about the system. And the new way of writing it, here it is. Here it is. We'll go back now and call this h. Let's call this h again. We have a new formulation of mechanics in which the time derivative of anything, it could be q, it could be p, it could be anything, is given by the Poisson bracket of F with what? With the Hamiltonian. That's all there is to the world. Every time derivative of anything that you can think of is just a Poisson bracket of that thing with a Hamiltonian. Of course, you have to know what the Hamiltonian is. This is the most condensed version of classical mechanics I know. I mean, it is really condensed. This is everything that you could, I can condense it even more. I'll condense it even more. Take this, subtract it, square it, call this thing say that it's 0, and then call this thing in here A, and then we only have one equation, A equals 0. That's Suskind's equation. In fact, you can write any equation, and you can take all of the equations of all of physics, take their squares, add them all together, set it equal to 0, and that's, this is pretty neat though. The time derivative of anything is the Poisson bracket of the anything with the Hamiltonian. Now, if this was all there was to it, then Poisson brackets wouldn't be all that interesting. But it's not. We're going to find out that all kinds of equations of physics can be expressed in terms of Poisson brackets. Symmetries, all sorts of things, that the Poisson bracket is a very central thing. And we'll spend a little bit of time. We're not going to spend a lot of time at that, but I just wanted to show you how it works. Okay, next time I'll tell you a little more about Poisson brackets. And then where I want to go is angular momentum. Angular momentum and how angular momentum works. Angular momentum is extremely important in quantum mechanics and throughout physics, and we'll spend some time learning about classical angular momentum.
For more, please visit us at stanford.edu.